Chemistry 1401, Practice Exam 1. Let's take a look at the solutions. Start with question number 1. It says, which answer is the correct scientific notation for the number 362.4? Well, since this number is greater than 1, what we're going to do is we're going to have to move the decimal place. So let's write it down, 362.4, and we're going to have to move it to the left 1, 2 places like this, and then we can express this number as 3.624 times 10 to the 1, 2. So times 10 to the power of 2. So it's the same thing as if you said 3.624 times 10 squared, which is 100, and that would give you 362.4. And so here's our answer, 3.624 times 10 to the power of 2. Question 2, which answer is the correct way to express 6.879 times 10 to the negative 3 in decimal form? And so this number is going to be less than 1, and so we're going to move our decimal place 1, 2, 3 places like that, and we'll put our decimal. And so when we write that number out as a decimal number, we're going to have 0.006879 like that. And so here's our correct answer, 0.006879. The next question deals with significant figures. Which one of the following values has 4 significant figures? The first number, 110, does not have a decimal at the end, and so this number has 2 significant figures. The next number has a decimal in it, and there are no leading zeros, therefore all the zeros are significant, and this number would have 5 significant figures. The number 9,000 only has 1 significant figure. We don't have a decimal on the end, and so we have 1 significant figure here. 0.224, the 0 at the beginning is what we call a leading zero or a placeholder 0. It is not significant, and so we have 3 significant figures here, but the last number, 55.5, has no zeros, and therefore all numbers are significant, and we have a total of 4 significant figures, and that is the answer. The next question asks us, which one of the following is an exact value? And so the first answer says the time is 11 a.m. Well, somebody might say the time is 11 a.m., but they might mean it's 10:59 or 10:01 or 11 a.m. and 20 seconds, okay? The trout I caught had a mass of 2.1. Well, you can see there's a decimal here, so that's definitely not an exact value. And the same thing applies to the third and the last answer, right? The mass of a nickel is 1.02 grams. Same thing here. That is not an exact number. We have a decimal here. Also in this temperature, 78.1 degrees Fahrenheit, that can't be an exact number. Whereas right here it says there are 31 days in August. Well, that's definitely an exact number, that 31, because the month of August is defined that it has 31 24-hour periods in it. And so 31 days in August, that number 31 is definitely an exact number. Let's try a math problem here. How many significant figures does the result of the following operation have? So we have 8.5201 plus 1.932 times 5.45. So we're going to follow the order of operations, and we're going to solve the bracket first. And when I take 1.932 multiplied by 5.45, I end up with 10.5. So 10.5. Now the question becomes an addition problem. And I'm going to set it up like this. I'm going to say I've got 8.5201, and I'm going to add 10.5. Well, you remember that in addition and subtraction that the final answer can only have as many decimal places as the number with the least decimal places. 8.5201, that's 4 decimal places, whereas 10.5 only has 1 decimal place, and so our final answer can only have 1 decimal place. And when you punch that into your calculator, you find out that the final answer is 19.0, and so that is our final answer, and that number has 3 significant figures in it. And so our answer is 3 significant figures in the answer for this operation. This question involves some metric conversions. Which of the following relationships is incorrect? The first one says there's 10 to the 3 milliliters in a liter. That's the same thing as saying there's 1,000 milliliters in 1 liter. That is certainly correct. If we look at the next one, it says 1 microliter is equal to 10 to the 6 liters. Well, 1 microliter is a lot smaller than a liter, so there certainly isn't a million liters in a microliter. In fact, 1 microliter is actually equal to 10 to the negative 6 liters, and so this would be the answer. This is the one that's incorrect. Let's just take a look at the rest of them. The next one, 1 gram is equal to 10 to the negative 3 kilograms. Of course, well, we know that in 1 kilogram there are 1,000 grams, so it makes sense that 1 gram is 1,000th of a kilogram. And then in the last one, it says that in 100 centimeters, there's 1 meter. Well, definitely, we have centi, and so there's 100 centimeters in 1 meter. Next question, tin melts at 231.9 degrees Celsius. What is this temperature in degrees Fahrenheit? So if we want to convert from Celsius to degrees Fahrenheit, what we do is we take our temperature in degrees Celsius, we multiply it by 9 over 5, and then we add 32 to it. And so when we plug that into our equation, we get 231.9 times 9 over 5, like that. And then we add 32 to it, and we get that our temperature in degrees Fahrenheit is going to be equal to 449.5 degrees Fahrenheit. And so there is the correct answer. Next question, ethylene glycol has a density of 1.097 grams per centimeter cubed. What volume would 2.64 kilograms of ethylene glycol occupy? Well, you can see that we're given our density in grams per centimeter cubed and our mass in kilograms. Let's take a look at our formula first. Density is equal to mass over volume. We can rearrange that to solve for volume, and when we do that, we get that volume is equal to mass over density. Again, we have our density, which is 1.097 grams per centimeter cubed, but I think it would be wise for us to convert this mass into grams. And so we know that there are 1,000 grams in a kilogram, and so we'll put in 1 kilogram, there are 1,000 grams. Here's our conversion factor. Kilograms cancel out, and we end up with 2.64 times 10 to the 3 grams, and now we can plug that number up here into our equation, 2.64 times 10 to the 3 grams. Look at this. Our units of grams cancel out like that. And when we punch that into our calculator, we end up with 2.41 times 10 to the power of 3 centimeters cubed, like that. And so here is our answer. Question number 9. How many square nanometers are in 1.82 meters squared? Well, the first thing you need to know that is in 1 meter, there are 1 times 10 to the 9 nanometers. And so we can use that conversion factor to help us solve this problem. So when we have 1.82 meters squared, we can use this conversion factor, 1 meter, and we know that in 1 meter we have 1 times 10 to the 9 nanometers, nanometers, and what we have to do is we have to square the whole thing. And when we do that, we end up with 1.82 meters squared multiplied by 1 times 1 is 1, meters squared is meters squared, and then we have 1 times 10 to the 9 nanometers squared, and that gives us 1 times 10 to the 18 nanometers squared. And you can see that meters squared cancel out, and we end up with our final answer, which is 1.82 times 10 to the 18 nanometers squared. And so our final answer is 1.82 times 10 to the 18 nanometers squared. Number 10, a graduated cylinder is filled with water to a volume of 44 milliliters. When an irregularly shaped solid piece of metal is added, the volume increases to 47.2 milliliters. If the piece of metal had a mass of 45.5 grams, what is the density of the metal? Well, for that, we're going to need the formula density is equal to mass over volume. We're already given the mass, which is 45.5 grams, But in order to determine the volume, we're going to use these numbers right here. And you notice that they have some kind of graduated cylinder, and they're putting some kind of, solid in there. And when they do that, the volume of the liquid rises from 44.0 milliliters. It goes up to 47.2 milliliters. And so the volume of the object is going to be the difference of those volumes. And so we can put the total volume is going to be equal to the final volume minus the initial volume. And so we have 47.2 milliliters, subtract 44.0 milliliters. And so our total volume is equal to 3.2 milliliters, 2 sig figs, sorry. And so when we put that in our denominator, 3.2 milliliters, like that, we end up with an answer 14 grams per milliliter. Now you notice that all the answers are reported in grams per centimeter cubed, but I'll remind you that in 1 milliliter, we have 1 centimeter cubed. And so we can also express this answer as 14 grams per centimeter cubed. And so we have the answer right here, 14 grams per centimeter cubed. The next question, what defines an element? Is it a molecule, a chemical symbol, a substance that consists only of atoms with the same nuclear charge, or a substance that consists of only one compound? Well, it's not a molecule because a molecule can be made of one or more elements, and so it's not a molecule. And a chemical symbol also doesn't define what an element is. If you look at the next answer, it says a substance that consists of only of atoms with the same nuclear charge. When it says nuclear, that refers to the nucleus. And if you remember what I said in class, what defines an element is the number of protons in the nucleus, and protons have a charge. So if you have a bunch of elements, doesn't matter the isotopes, if they all have the same number of protons, that means they have the same nuclear charge, and they will be the same element. So that is what defines an element, is the nuclear charge, the number of protons in a nucleus. The last answer, a substance that consists of only one compound. Well, that certainly isn't the definition of an element. A compound is a substance that is a heterogeneous mixture of elements. No, it's definitely not a heterogeneous mixture of elements. Can be broken down into two or more simpler substances. Well, we can certainly break a compound down into two or more atoms or simpler substances, or ions, maybe polyatomic ions, can be separated into its components by filtration or distillation. Well, that's a physical process, or those are physical processes, I should say, cannot be broken down into two or more simpler substances. So a compound is something that can be broken down into two or more simpler substances. An example would be water, which is a compound, and by the process of electrolysis that I showed you in class, which is passing a current through water, you can break it down into hydrogen and oxygen. Question 13, what is a molecule? Is it an aqueous solution, a particle consisting of two or more atoms joined together, an atom, or a heterogeneous mixture? Well, molecules are made of atoms, so it's not an atom, and it's definitely not an aqueous solution. An aqueous solution could be a solution of a molecule in water, of course, which is another molecule. Anyhow, in a heterogeneous mixture. Well, a heterogeneous mixture is going to be composed of more than one type of compound. And so a molecule is actually a particle that consists of two or more atoms joined together. For example, you could have a molecule of, let's say, bromine, so that's two bromine atoms joined together. That's one of the diatomic elements, and so you have a molecule of bromine, or maybe carbon dioxide, that's also a molecule. It's composed of one carbon and two oxygens. Number 14, what is an ion? An ion is a charged atom or molecule. Remember, when you have a positive charge, that's a cation, and when you have a negative charge, that's an anion. None of these fit the bill of an ion, an electron, a gamma ray, an isotope, or a molecule. So an atom or molecule with a charge is an ion. Next question, which of the following is not a possible property of a mixture? Well, a mixture certainly can be separated into its components. If you have a mixture of, salad with lettuce and tomatoes and olives, well, you can certainly separate those. You can separate them. It can be homogeneous. A mixture can be homogeneous. A mixture can also be heterogeneous. But a mixture cannot be a pure substance because a mixture is made up of two or more substances mixed together.